Well, in addition to using expected counts as this response unit of our interest, we can also use predict probabilities for discrete change and discrete rates of change. And as laid out in one of our previous slides, the predict probability for a count, okay, here, for a count, given x, okay, given x here. So this is a count, this is given x, is equal to, if you remember, is the exponential function of negative mu multiplied by mu raised to power y. Y is the count of our interest to calculate the probability, right? That is the probability of having certain count, although we only observe one realization of count for a respondent or for a case or observation, but the probabilities for different counts still exist. Okay, so that's what's in the numerator. And in the denominator is y factorial. And here, mu is the expected count, is equal to the exponential function of x beta. So it varies, right? Varies with different x vector, you know, because here, different cases going to have different x vectors, and different cases accordingly going to have different mu. Okay, so the probability for having the same count given different x vectors, okay, going to be different because the differences in covariance. So in this case, again, P, y given x is the conditional predict probability given xk is equal to x subscript s, okay, the starting value of x, okay. And another predict probability, okay, y given x is the conditional expected rates given xk, this generic variable, is equal to x subscript e, okay. Note that here, y, or counts for these two predict probabilities, need to be the same. And otherwise, this discrete change is not meaningful. We're not supposed to take a difference between two predict probabilities of different counts. Let's say the predict probability for y equal to 6 minus the predict probability for y equal to 4. That's not substantive meaningful, and we don't do that, you know, frequently for good reasons. And let xk, this generic variable xk, change from x subscript s to x subscript e. Then the discrete change in predict probabilities is equal to the difference of these two predict probabilities, given xk equal to x subscript s and xk equal to x subscript e, and holding all other covariates at given values of our interest. Okay, so here in this case, we're going to say, well, for a change in xk from s subscript s to x subscript e, the predict probability changes by delta p, you know, for this count, the same count of y given xk. Okay, excuse me, given x, okay, holding all other variables at given values. So in this case, we just measured the difference in a generic variable xk. We're not supposed to vary the values of multiple covariates because otherwise such comparison is not going to be that meaningful. And then we measure the difference in the predict probabilities, okay, for the same count, okay? Have to be the same count, now, given these two different x vectors. Similarly, Similarly, we can also calculate discrete rates of changes in predicted probabilities. So in this case, discrete rates of change for a change of delta in xk. Again, a generic variable xk equals, okay? Again, a ratio of delta p, that is difference in predicted probability, over delta xk, a generic variable xk. And on the right-hand side of the equation here, we can see that that's a difference in these two predicted probabilities we just talked about in previous slide. And in the numerator is the difference in these two x values for xk, okay? So this can be interpreted as xk changes from x subscript s to x subscript e, we would expect the discrete rates of change in the predicted probability is roughly this ratio, delta p over delta xk. Again, this comparison is only meaningful for the same y, same count. Okay?